All right. Hello, this is Stephen with Shield Digital Design, and today I would like to demonstrate the Cadence Sigrity Aurora DCIR analysis flow right here within Allegro. So what we've got is we've got a BeagleBone AI board here, but we've got some modifications on here. We want to check and see if the power delivery network has been designed adequately, and let's look at this next generation hypothetical CPU, right? We're not going to look at the exact device properties. What we're going to look at is this hypothetical processor has a 1.15 volt nominal core voltage, and we'll say it's got a 3% tolerance, and let's say we're drawing 8 amps on it. So what are we going to do to make sure that we've got an adequate design? So in this particular board, the voltage regulator module is this power management IC right here. And this device has two outputs, a dual phase buck converter, and that's coming in right here and right here to these parallel inductors, L1 and L2, and their output is shared. They go through this set of vias down here. We're going to drop down to layer 6, and it's been routed over on layer 6, and we come up most of the way, and then we realized that we had something in the way. Maybe we, for some reason, had to jump over to another layer, it looks like. And so we see some more routing on layer 10, and then back up through these vias into the device. So one of the first things I like to look at when we need to look at this type of analysis is just the stack up. We want to make sure that the stack up has been entered into the design tool in accordance with how it's going to actually be fabricated. So what we see here in this board is that we've got power planes with 1 ounce copper, ½ ounce copper on the rest, and then 2 ounce copper after plating on the outside. Now, the copper thickness is what's really important for a DCIR analysis. Dielectric thickness, not as important, except for two things. If we're going to look at thermal analysis, we'd really care about dielectric thickness as it impacts heat traveling through the board. And also, if we were going to look at a PDN analysis in the AC domain, looking at the impedance over frequency, then we would certainly care a lot about getting all of the dielectric layers correct as well. So, if that's been done, we're going to shift over here to our analysis. Now, the way we do this, analyze workflow manager, and we'd want to make sure our DC nets are set up correctly. So in this case, I know I've got VDD MPU set here for 1.15 nominal voltage. All right, and then when we want to do our DC analysis, we have some options if we want to adjust default properties or look at current density thresholds, make those changes. That's something that can be done here. We have the option to just manually set up VRMs and sinks, and that's very nice if we have a very quick, simple architecture. We want to just check something real quick. We can set our VRM, set our sync, and run it. Or in this particular case with our dual phase buck converter, we're going to use a power tree file. So I've got a power tree set up here. And in this case, we've got U3, that's our power management chip, set with its two different phase outputs. We've got series inductors here and here. We're going to ignore any DC resistance in these inductors because, of course, in reality, we're going to see a switching waveform here. But in this case, we're just going to set it as a DC output and see what happens. Now, what you can see here is the bottom U3 is actually connected through this net to L2, and they both go out to U4. Now, U3, this is a feedback pin. We can go ahead and disable that. We've got U4 set for our 8 amps, worst case current draw. We can go ahead and look at some of our properties here. Nominal voltages 1.15 in our VRMs. Our sync here, let's just tweak that to make sure we've got a 1.15 nominal voltage there, so everything's in agreement. We can double check that our discrete series components have no resistance because we're just ignoring that property for now. We'll go ahead and save this here. Make sure we're in the correct directory. Yes, we are. And let's load it up. So we'll set our power tree file and kick off the analysis. Now, one of the nicest things about the power tree file is that if you've got a very complex topology of many different power rails, you can enter all of that in the power tree file. Use the power tree as sort of this master document where if changes need to be made to things like the sync current or voltages, You can easily make it there without having to mess with anything here in the layout file. So analysis is complete. Let's check out our results. To start with, let's just look at the voltage table and see if our sink is getting adequate voltage. So with that 3% tolerance, we're looking for 1.12 voltage, 1.12 volts at the input pins. And we can see here, I see a lot of pass fails showing as failures. Looks like we are just marginally under our 1.11, 1.12 volt threshold. So maybe we can make some very minor tweaks. So how are we going to determine where to make those changes? One of the ways we can do it is just look at the voltage overlay. Very nice here. We can look at the top layer. We don't see a ton of drop here on these short runs on the top layer. Maybe a little bit here where we've got some gradient that we can adjust for. Remember, we go down to 6. So let's look at 6, and this shows us one of the major issues that we're encountering. We've got this very large voided area due to these vias, and we need some way to get current from the left side over to the right side, and we're probably pinching a little bit here and here. We could adjust that. And then lastly, let's see what's going on layer 10. Again, we see a decent amount of voltage gradient here, probably 20 or 30 millivolts from the bottom of this shape to the top. So what we can do is we can just very quickly make a few changes. So let's do this. Let's jump down to layer 6. Maybe we know that we've got some room on some of these adjacent shapes that we can just squeeze things up a little bit. So what we're gonna do is we're just gonna make now, one thing I didn't mention at the start here, but one thing I really like to do when checking out these type of analysis is just take a quick look in the 3D canvas at our net individually, and we can get a good idea of what's going on if maybe we made a transition where we shouldn't have, or where it could have been better, or where is there some parallel copper. Like right here, we can see very easily we've got, now that we modified layer 6, we've got some parallel copper on these 2 layers. Just checking things out in 3D gives you a good overview, something that you can't always get in a 2-dimensional view. Here we can see our feedback pin back to U3. So let's rerun our analysis. So we'll go over to the airdrop workflow. We've already got the same power tree file loaded. Nothing changed in the power tree. We can just go ahead and start our analysis. We'll discard our previous results. All right, so let's take a quick look at our results here. We'll pop up the voltage table, and we can see that we're passing, and just barely. Looks like we're at 1.12 volts, 1.126 on all of our pins. So that's about 10 millivolt margin on our worst case scenario here, 11 millivolt margin. So let's just take a quick look at our overlay, and we can see we made some adjustments here, a little bit less voltage drop there. We really widened up this plane. Less voltage drop on layer 6. We can even look at our current density to see where we're getting some hot spots. You know, maybe if we wanted to even do some more optimization, we could here. But the point being that we've hit the minimum voltage threshold that we need, and if we needed to do a little further analysis, say a thermal co-simulation to make sure we weren't heating up traces or components beyond where they need to be, we could do that. But we've done a ton of analysis, a ton of checking, just to make sure that the next step can go on smoothly, and this really helps with reducing back and forth between somebody doing layout, somebody else doing analysis, things like that. So thank you for watching and checking out this video, and don't hesitate to reach out if anybody has any questions. Thank you.